Mhm. Okay. Uh, yes, yeah. Let me. I've not actually read them, but I just saw that it's. Yeah. So let's see. So we have the unit disk, the closed unit disk, and identify S1 with the boundary of. No, I'm just reading. I just write. Define an equivalence on D2 by declaring any 2 points in S1 to be equivalent. The resulting quotient space is this, and prove that this is this. Okay, let me. Yeah, I suppose, yeah, intuitively it's clear. So, but. Mhm. Uh, Wait, but the unit circle is not homeomorphic to uh, the unit circle is homeomorphic to what? You said this? No, this is not possible in the quotient topology. But what topology is there on this? Uh, okay, all right. Yeah, and this problem is precisely a generalization of that. Right. Yes, yes. So this is basically D1 quotiented by S0 because S0 is the boundary. Right. But usually, I mean, usually this is it. If I interpret it as a usual topology, then is it's wrong, but obviously it's correct with the quotient topology. Yeah, so you're saying that, yes. So how do you prove this, this second one? Mhm. Okay, right. Okay, so put the uh, right. So you put the quotient topology. Okay, um, and then how do you say that it becomes a isomorphism? Uh, right. Just a second. Yes. Yes. So you have this, and maybe we should, yeah, just call this X, and then by uh, universal property, you have that X is homeomorphic to S1. Yes. So, right. So, let me just, since Vaishnavi has joined, I just introduce the question. So, Vaishnavi, see, I'm just trying to solve this question. Okay. Um, First, this one, that S1 is homeomorphic to the unit interval with the two endpoints identified, where S1 is S unit circle. And for that, we define this map from this close 0, comma 1 to S1. And then you just put the quotient topology on 0, comma 1. And Mahima, can you just state the universal property? I think that will be. make things clear because we are going to also use it later. So yeah, maybe yeah. Okay, right. Okay. Hmm. Okay. So y is equal to uh, q inverse z. Yeah. Yes. Yes. But uh, but the set y is not clear yet. What is the set? Maybe I'll just write on a new page. Okay. So yeah, because this is the what we will need to the other problems also. So universal property of uh, of quotient of I'll just say quotient topology. So you're saying that okay, if you have x and z and you have an arbitrary, but why do you want this map to be a quotient map? Okay, let's take it since you're saying, let's see, q be a quotient map. Yeah, and then you took y, but I am still not clear with the y. So okay, so you're saying that this q inverse z is a point. Okay, okay. So that is y, and what is the topology on y? Right. Mhm. No, you see, this y itself will be your z. Oh no, yeah, right. So this doesn't look like because this y is basically same as z, right? Because for every point in z you have a point in y, and I suppose you will give y the quotient topology induced by some map, induced by a map, and that map is we can see what it's going to be. It will send q inverse z to z, but then it's just q. It's q and y is just z, right? Because what does it mean to say that q is a quotient map? It means that z has the quotient topology. It means that the topology of z is same as x quotiented by these things. Yes, but then there should be something more than this to universal property of quotient, right? So the universal property will be with respect to some other maps, right? Means with respect to arbitrary maps, arbitrary up to the extent that you have to take a continuous map, right? Take a continuous map, and yeah, maybe yeah. So one map you take one map to be, you can take quotient map. Yeah, one map will be quotient, but the other one has to be a continuous map. Yeah, or maybe we can stick with the notation you are using. So yeah, but then this one you have to take to be arbitrary, right? And then what does the universal property say? Okay. So there exists a unique map. Um, from Y to Z, but when? So, Q is a quotient map, so Q will be continuous, and F is continuous. So um, you need to say that the fibers of this contains the fibers of Q. Mm, So for all Z, there exists Y such that this thing happens. So sorry, if this thing happens, right? This is necessary, right? Because if you take a Z and you're pulling back the Z, so you take a point Z and you're pulling it back, then you get some things. Now all these things must be mapped to one point only. Is that no? Wait, am I correct? Yes, if there has to be an inclusion. So let me see. So you have this map Q. Okay. So it's because this direction was wrong, right? There should be a map. There should be a map from the quotient topology. Yes, there should be a map from the quotient topology. And now, why is there an inclusion? Because um, yes, because so yeah, so you want to factor f, right? So if 2 points are going to two different points, right? Then they must go to two different points here under Q, right? Otherwise, you cannot factor it, right? Which means that um, so there has to be an inclusion, but what will be the direction? Yeah, it means that if 2 points are going to the same point here, right? Which means that if 2 points are in the fiber, then these two should go to the same point. So just I should write it. So for a map, even set theoretic map to exist, right? Given Q, and now you're given F. Now for a set theoretic F tilde to exist, it is necessary that Q inverse that it is necessary that um, at Qx equal to Qy implies that f of x equal to f of y, right? Is a necessary condition, is necessary for f tilde to exist, right? Which basically translates to saying that the fibers of Q are contained in of fibers of Q, so some Z are contained in fibers of Y. So it's a necessary condition. And the key thing here is that it's also sufficient. So if this condition is satisfied, then f tilde exists. Okay. And that is and proving that is nothing. I mean, that is just from the definitions. Mm, But I'm not going to prove it, but you want, you can prove it later. Yeah. And then there is more. Of course, f tilde is continuous and so on. But if if f is a quotient map, if f is quotient, then F tilde is also quotient. F tilde uh, is a quotient map. Yeah, this is another fact, right? How do we see it? So um, yeah, let's try to see that. So you take, but let's try to prove that F tilde is. So we're just doing it verbally, okay? Try to show that F tilde is quotient map. So you take you take S in this, right? Take the inverse image, right? Assume that it is open. You want to show S is open. So how to do that? Well, I mean, this is open implies that its inverse image under Q is open because Q is continuous, right? But this is open implies S is open because F is quotient, right? And this is same as F inverse S. This is same as F inverse S, and F inverse S is open because F is a quotient map, and so we are done, right? No. Sorry, yeah, we are not done, but we are done. But I need to say something. So we have proved that this is open, but that implies this is open because Q is quotient. Yeah, I did not say that. Yes. Okay. So all these are fine, but it's important to, yeah. So this is a universal property. Yeah. So is it fine? Yeah. Yeah. So it's very simple to remember, of course, but yeah. Okay. So now let's move to the problems and then we will see if now the problems become easier or not. So let's go back to the first problem and see. Yeah. S- So we want to show that this is S2. I just wanted to say one thing that yeah, in the D1 to S1 case, you could construct an explicit map. In this case, of course, you can also construct an explicit map, but let's see. Um, right, okay. Yeah, that's correct. Upper hemisphere of S2. And yeah, that's right. Hmm. Yes, that's right. Proof is, yeah, I mean, intuitively it's fine. Yes. So to make it, I'm saying the same thing, but maybe just slightly more calculations. Maybe you could say. So you have to just define a map. So um, right. So you take S2, but you take S2, you translate S2. So you take S2 with the south pole as the origin, and now of course, so with the same coordinates, you take D2, right? And then you have to define a map which folds this D2 up, right? To define that kind of map. And you can explicitly write it, and let's actually do it. Oh no. So no. Sorry, there is a okay. So if you do what is called a stereographic projection, right? So so we are trying to define a map from S2 to the plane, or from the plane to S2. So if you just take a point on the plane, not necessarily in the disk, okay, and just take this point P in the plane. So plane meaning P is in XY plane, and we join it with this point north pole and 1000, and then look at the point where it intersects, right? That gives you a 1 1 function, right? And so that, yeah, it's a stereographic projection, right? Because it's just yeah, this map, and this map of course you can explicitly write down. Okay, so what this is giving you is a map from, yeah, it's giving you a map from R2 to S2, right? It's giving you a map from R2 to S2. But let's try to be slightly imaginative and see if we can get a map from D2 to S2. Now it's just that you have to just shift things and check. So let's see. Yes, yeah, meaning, yes, you can certainly go in that direction, but I'm just trying to do it without that. Just for a minute, and then we can go there. Yeah. So let me see just if it is if it is possible to directly do a projection and get it, because you see, like it's like, so it's just this, and you have to just fold it. So there should be a folding map available. So just what should that look like um, is yeah, I mean, so you have to kind of take this, let's say this line, which we know what it is, and we have to just map it to this semicircle, right? And you can just write an equation for this, right? So so this is the x-axis, and this is the y-axis, and this is the z-axis. I mean, yeah, I know we'll get to that method. That method is better. What you're saying means it's more topological, but you see, we can just write an equation for this map, which takes this line to this semicircle. We can just sit and write that. It's not a problem, right? And then you can just do that for every rotated semicircle, like this, for every rotated whatever. I mean, yes, you have to just take this thing and you have to just circle it. So why don't we just write the map instead of just, I'm just saying. So let's just write the map. So if you if you take a t comma 0 comma 0, I should, where should I send it to? I should send it to uh, cos 2 pi t, or so here it's going from minus pi to pi, so cos 2t 0 sine 2t, right? This map sends line this line from -100 to 100 to the circle, to this desired circle, right? And then you can obviously, using this, you can define the general version also, right? If it's just an arbitrary line, it will it will we are no, yeah, it's inside R cube, but I am taking a map from D2 because I want to go get a map from D2 to S2, right? And so far, yeah, and you can see what I'm just doing, map from D2 to S2. So far I've taken this pink line segment in D2, which is from -100, this point, to 1000, 100. Yeah, sorry. And then you just fold it. And I've given an explicit formula. I mean, this is just written it, right? And you can do this for every line. Instead of this line, just rotate it and do it. Right? Yeah. Is that right? I mean, if you just multiply this with some e to the power I theta kind of thing to the first two coordinates, and then apply that same thing to this and this coordinate, right? And that will just give you a map, correct? And then so what you will have, you have this surjective map, and in this map you see that S1, this S1 is going to this north pole, but yeah, you have to then just prove that this is a quotient map, right? And that I think that's why this version you were stating was like that. Right. What you right? Yes. Yeah. So what you have to just prove that this is a quotient map, and then of course by definition there is a map from here. So this is, you have to prove that this is a quotient map, and maybe I will call this quotient canonical quotient map to be this. And by the universal property, there is a map Q tilde, right? And this Q tilde is also a quotient map because the original map was a quotient map. And now you have a quotient map, which is also injective, so it is a homeomorphism. Yes. And so you get what you wanted through an explicit map. And you can just, even if it's dn, you can just actually mimic this kind of thing there also. Yeah, it's not a big deal. But let's get to let's try to do it in a different means the way you were suggesting. So hopefully this one is clear. So yeah, let's just do it on a new page. So what is the method that you were suggesting? Hmm? Um, yes, and that is what exactly, and that is what the stereographic projection shows, right? That this is actually homeomorphic to the sphere without the point, without the north pole, right? Because if you see, this is what the stereographic projection does. It takes, because I'm using that D2, open D2 is homeomorphic to R2. So we have this, and this thing is homeomorphic to this by the stereographic projection. And so we have this. And stereographic projection, again, you can write the equations explicitly. And it's homeomorphism, everything. So you can get that. But then what do you do? Then how does this prove? Right. S- Yes, their one point compactifications are homeomorphic. So that's right. So you're saying that if X is homeomorphic to Y, it implies that the one point how what should be the notation of one point compactification? Uh, Maybe X plus X union infinity. Yeah, that's better. Infinity is homeomorphic to Y union infinity. But just a second. So, Vaishnavi, do you know what is a one point compactification? Might not have studied. Yeah, cool. So, but yeah, so we will deal with this. Okay, so X and Y are locally compact Hausdorff spaces, but then you should tell us what is one point compactification, maybe. Hmm? Right. So I think that is a fine. That's okay. That definition is fine, and it is unique up to homeomorphism. There is there is of course more in some sense. Probably this is the only thing, but yeah. So with that uniqueness, we get that the one point compactifications are also homeomorphic. Why does it exist and so on? We can talk about it later. Yeah, means after doing this problem. Okay, so but then what is the one? But then how do you prove that the one point compactification of this thing is S2? How do you show? So the task now is to show that uh, one point compactification for which we have notation. So we will use that. So show that this is same as S2. No, I am sorry, I'm writing something wrong, right? Yeah, that we have shown, that we have shown. Yeah, what we want to show is possibly this, maybe, that the one point compactification is this. This is what we want to show, right? So if we show this, then we are done because these two are homeomorphic. So their one point compactifications will be homeomorphic. And the one point compactification of this is, of course, S2. And so, yeah, so this is homeomorphic to this that we already know. Now we need to show this part so that everything. So now, Maima, now you should use universal property of one point compactification. Then it should come. Means then you should frame it because you can just frame it. I think. I mean, I don't remember, but you can. So what should it be? So it should be that if X is a locally compact Hausdorff space and oh yeah, maybe so. Oh, uh, yes, X is locally compact Hausdorff space, and let's say that. Hmm, no, I think yeah. So yeah, maybe I will not say universal property. I should not say universal property, but I should just say like this, that suppose that X is sitting inside a space Y such that Z is compact and IX means the inclusion. So the image of the inclusion Z minus this, um, I should say, is a point, right? And of course, these are just technicalities that X is homeomorphic to IX. This implies that Z is homeomorphic to the one point, or I think it's also called Alexandrov compactification X. Yes, and let's just let's um, prove. I mean, so yeah, so let's not prove it, because I think we have to then state the one point compactification definition very clearly. Means that how the topology is defined and so on, which of course it can be done, but let's not do it right now. You can prove this later. Okay. And Vaishnavi, you can just read up a little bit of one point compactification and then try to prove this as an exercise. Okay. Yeah. So Moncrief is a very good place to read uh, one point compactification. Yeah. That's the only compactification I know, and stone check compactification. Other than that, I don't know any compactification. There are many like nice compactifications. Yes, in fact, the compactifications is what leads to study of moduli spaces. Also, it comes, but yeah, quite ignorant to that. Okay, okay. So how do you? And now this problem is basically done, because um, oh, yeah, is it done? Uh, uh, hmm. Yes, but why will it be continuous? So then basically you are yeah. Then to show continuity, you will be using the definition of one point compactification to show the continuity, right? But can you just quote use this property? I mean, this is playing with this kind of. If we have a property now, we just use it. Just exercise. So as you understand that um, that the in that the should just say, yeah. So basically the quotient map. So just to use that property. Otherwise, you can do this, but just to use the property. So you have this map, right? And now you take this map and you restrict this Q onto the open disk, right? This thing. And yeah, and then you basically, upon this restriction, you get a map from here to here. And basically this is playing the role of your I, and this is your X, and this is your Z. Then by that property, it's a one point compactification, right? Because Z minus the image of the open disk is only a single point, and Z is compact, blah blah blah. Yes, but what you're saying is also you can do it like that. That's same thing. But also when you say these things, it's one point here to make, that you can also try to prove this. Basically, f is a map from x to y. The question is, and let's say there is this map, there is this one point compactification, and there is this inclusion map. When does there exist a map? When can you extend a continuous function from uh, uh, sorry, when can you, okay, sorry, it's wrong. Extend, so yes, yeah. And the question is, when can you extend it from the one point compactification? Okay. Yes. Basically, while proving this, you will be encountering that. But if you can isolate the condition, you can identify the condition, then it will be nice. Yeah. Maybe I will not say it right now. You can think about it. Yeah. And basically, this is the thing which, like, people say that, okay, then you cannot extend every continuous map. You can give examples. You cannot. So obviously, uh, uh, obviously, no. Yeah, I mean, obviously, like maybe the image of f has to be compact and so on. That is fine. Uh, yeah, so maybe y has to be. No, y doesn't have to be compact. But yeah, I mean, the point is that not every continuous map can be extended, and that's why one-point compactification is lacking in that place. And that is why we have something called stone check compactification. So that's much more involved, and yeah. So there, all the continuous maps can be extended, provided, of course, that this is a compact space. Okay, so or yeah, we can, since it's not in the context right now, so we can do it. Yeah. So that's the problem, and let's. So should we try the next question? Yes. Okay. Yes. Right. Just both the proofs can be extended, but yeah, yeah. The second proof, you see, somehow avoided all the calculations. That is quite nice. Yeah. That both the things that we are constructing is a one-point compactification. So okay. Okay. So the next problem is about the real projective space. So we need to show that um, dn no, what am I doing? Dn with a unit ball define an equivalence relation on X by declaring this on the boundary. Okay, so how is this? Yes, of course, yeah. So dn, and then you say define this relation. You say X is equivalent to minus X, but only on the boundary, not everywhere, only on the boundary. And we want to say that this is same thing as the uh, real projective space, and it is n. That's the question. Yeah. So again, this is an exercise in quotient topology. So that's what we are doing. And yeah, but maybe you should define the real projective space. We should have one clear definition of the real projective space. That will be, yes. So how do you define? Okay. Hmm. Okay. And lambda, right. Okay. And then, right. So we have that definition, and yeah, so, so it's just good to have a definition. Yeah, so just write this much. Okay. So with that definition, we now need to get this definition. Hmm. Okay. On Sn, right. Uh, okay. So this also gives you RPN. So how do you, are you assuming this or you're going to prove this? Okay, right. So let's assume this for the time being. This is actually easier, follows almost from the definition, because yeah, lambda just becomes plus minus one. So we assume this. Okay. Yes. Yeah. Mhm. Right. I agree. Yeah, that's what we should be doing. So I think it's fine because you just take Sn and you flatten it to Dn. So you take, yeah, then that's all. But we still see everything fits. So Sn going to Dn is the flattening map. Just flatten it, and yeah. Can you just say what the map should be? It's better to write that. So we just write x0. No, I think so. Whenever we are writing these coordinates, we should write like this: xn, and I want to send it here, Tn. So yeah, so I think I just forget the last coordinate, right? Yes, yeah, that's what. Yeah, so it's just yeah. So maybe better to just write projection map and yeah. And this is a quotient map. Yeah, no doubt. You can prove it if you want. It's a quotient map. Uh, right. It's yeah. Mhm. Right. Why it's a closed map? So why is a surjective map from a compact? Uh, yes, should be closed surjective continuous implies quotient. Yeah, should be because if you let me just check. Let me just verify it. See, so if I take an open set, then so if you just take a set here and you pull it back, or maybe you take a set and pull it back and say if it's closed, then its image is, yeah, it just follows from the definition, right? Oh, really? But then no. So if I just take S and I take Q inverse S, and if Q inverse S is closed, then implies S is closed because it's a surjective map, and so the image will be S. And yeah, so open will also imply quotient, right? I mean, not cross, but open will also slash slash open. Yeah. Okay. Okay. Yeah. So nice. Yeah. And it's a closed map because it's from a compact set. Right. Um, yes. Yeah. All that things you have to do. So means proven then. So this is the quotient map. So it's a good thing. It's probably also covering covering map. It's also locally it's a homeomorphism, which is also clear. So yeah, or 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 is it no? So just yeah. So this one, you're asking why is this a local homeomorphism? Right. Yes. 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 Yeah. It is not a local homeomorphism. I think. Yeah. I'm wrong. Yeah. It's not. Yes. Because near the equator, if you take a neighborhood around the equator, any point on the equator, then it's you cannot. It always is not injective there near the equator, right? Because yeah. So just seeing if I'm correct. Like if you take this, you flatten it, then of course it's not. Yeah. So, anyways, it's not a. I was going to say it's a covering map, but then it's not a local homomorphism. Okay, so it's a quotient map. That's all we need. So, right, it's a quotient map, and so now you just further quotient it by that relation. So let's just call this x, right? So this x, and so composition of quotient maps is a quotient map, right? Hmm. Right. So this is also a quotient map, and then you of course go to this, maybe just yeah, writing it. Go to this, and now you just check that it becomes injective. Becomes injective, right? This map becomes injective. Yeah. Oh, or wait, am I? Yes, this map becomes injective. So I mean, here you have like x and minus x, and they are going to the same point. They are going to the same point, and so oh wait, something is wrong. Ah, no, it's because this is wrong. This is not the case. Yeah. Yes. So what is happening is, of course, the projection map. So in the projection map, um, I should just maybe say that Sn minus, how should I write it? Sn minus Rn. So I'm just saying that like those uh, that the part of Sn uh, in which the last coordinate is positive, right? So that part is taken care of, right? And so the way to say this is just this. So you take Sn and you take intersection with Xn um, not equal to 0. This is one part. And of course, the other part is when Xn is equal to 0. Okay, right. Okay. Yeah. So when you take the quotient, right? So now let us just analyze this. So I mean, see, pictorially is very clear, I think. Right? So, but the point is to be able to convert those arguments into intuition into the thing. So yeah. So the point is that if you take any point uh, in which xn is not equal to 0, like so, if you take if we take this part, then this part is of course going to the interior, right? It is surjecting onto the interior, right? And Q there is 1 1 actually. Okay, and so Q is 1 1, and so the pre-image for any point x here is just 2 points, right? Xn minus, well, I mean, x, not xn minus x, but it is x comma some square root thing, right? And then yeah, x comma minus square root thing. The point is that there has two pre-images. Let's just take that, right? So this just has two pre-images, and those two pre-images are getting identified in this, and so those points are taken care of. So it's injective on that. Okay, so Sn, so this map Q composed by restricted to this part is injective, uh, right? Yeah, maybe I should not write it like this, right? So in that part is it is injective. You've taken care of that, and in the other part you can, and the other part is also taken care of, right? Because it's taken care of in Q. It's injective. Pi is injective there, right? Pi is injective on this, and so it's fine. So it's, we are done. It's the same kind of thing. So it's really not much. Okay. Yeah. Okay. So that's okay, I think. And last problem is, I think will be, so let's maybe read it. So yes. So I think now you should be able to do the last one also, right? Because this, but some, yeah. Try it. Right? I think Vaishnavi, you should also try it, and then you see what happens. Yeah. Two copies of it. Yes. Yes. Right. Yeah, yeah. Identifying the boundaries of D1 and D2, but identifying means that in the just a natural way, right? So yeah, the corresponding points you are identifying, right? So it means that, like, so you have one copy of D2. So that as you already observed, that it's the upper hemisphere basically, and the other copy of D2. So you think of that as a lower hemisphere, but these two are identified in the natural way. So like this point we can identify this point, and so on and so on. So yeah, because if you identify it in other more interesting ways, then you may not get a sphere. Right? You may get some twisted object, right? I mean, of course, I mean, as long as it's a homeomorphism, also it's fine. In this particular case, it's fine. So this is basically S1 and this is S1, and it's fine. Yeah. In this case, it is fine. And you can just prove a general fact. You can also see what the general fact should be, right? That if you take dn and dn and just take their boundaries, which is Sn minus 1, and glue them, then you get Sn, right? That is what it is. Yes. Yeah. And yeah, this kind of why this kind of gluing, you may think, so, right? So why are you building Sn by using two copies of dn? What could be the advantage of that, right? That is the, I think that is more pertinent question. Yeah, right. So it's like you already had Sn minus 1, okay, and then you brought in two copies of dn and you identified it, uh, maybe, right? So you have two copies of dn, and then you bring in an Sn. You had an Sn minus 1, you have two copies of dn, and you are identifying it by the, just at this boundary you are identifying with Sn minus 1, and you're doing it for both the things. So maybe di, I should say, I going from 1 to, right? And this way you are getting Sn, right? And you can kind of imagine that this is an iterative process. Sn minus 1 also you can build in the same way. Okay? So you start with uh, you start with S0, which is 2 points, right? That's just S0, and then you bring in two lines, and you start with 2 points, you bring in two lines and you build this, and then you bring in two disks and you build S2, and so on and so on. So yeah. Yes. Yes. So yeah, so this is the CW complex structure on SN, CW complex structure, and W is for weak topology. So that we can see why it's called. And C, actually I don't know, is it called or compact, or maybe when you read you can tell me next. Yeah. uh, don't remember. Yeah, but it is a CW complex structure, but it is more than that. It is that, but it is more than that. It is should be a Z2 equivariant CW complex structure. And why am I saying this? Because yes, because you see, it's a special one. So obviously, if SN, you can give other CW complex structures, like the first thing that we discussed, right? That is basically taking maybe this is C for cells or something. Yeah, maybe just to guess. As you just saw, as we just saw in the first problem, that you can just take a point and take DN, and with that you can just build SN, right? Yeah. You can just build SN by identifying the boundary with the point. That is also a CW complex structure by the definition of CW complexes. Okay, which we don't have an official definition, but it is. Basically, you have to take the boundary of the new thing that is coming in and identify that with the old stuff. You cannot identify the interior of the new things. That, but that is one decomposition. Cool. But this is a Z2 equivariant decomposition. Why we are saying this is because if you let Z2 act on Sn, or in the language that we are doing, if you take this map which takes x2 minus x, right? And then you quotient by the orbit of the map. What is that? That is basically quotienting Sn with the relation x comma minus x. And that you can see is a Z2 action on Sn, okay? Where you take x2 minus x by the action. But anyway, so it's a Z. Now, why is this called Z2 equivariant? Because if you take this CW complex decomposition, then the action, so now we have an action, right? The Z2 is acting on Sn, where 0 of Z2 is acting by identity group action, and the 1 of Z2 is acting by x going to minus x, right? So under that action, you see that the cells, now these are called the cells, these things which you are bringing in, these DIs, and even this Sn minus 1 can be made like that. You see that these cells are basically getting permuted, right? Yeah, so under this, for this particular CW, for this one, that's not the case. Okay, but for this CW complex decomposition, the cells are getting permuted in a very exact way. What does it mean? It means that if you, well, now I can start to write, if I write these things in terms of a push out in the category theory language, things become more clear. But if you want to just say it right now, then what it means is it's still very simple actually. If you now quotient this by that action, meaning just quotient Sn by x comma minus x, identifying s comma minus, that's called quotienting by a action. The orbits become points. Okay. Then what happens here, as you know, things remain intact. You only get one di. Is that right? Yeah. Because, right, I mean, two copies and they were getting permuted. So when you quotient, you only get one copy. Okay. And so we get this. So we automatically get a CW complex structure for the real projective space. Okay, so you see, because now you have a real projective space, right? This is the real projective space that's what we proved. Okay, and this is the official CW complex decomposition because it matches the definitions, and you can also see that it has the same kind of form, right? And so this is the benefit of having a equivariant decomposition. Okay, yeah, that if you have any because it's like if your object is some quotient object and it is made out of some object like Sn, if something is made by quotienting Sn, right, then you would want a CW complex structure on Sn so that quotienting that complex structure, CW complex decomposition, this cell decomposition, directly gives you the decomposition for the quotient. That will be great, right? And so that's why these decompositions are very nice, and they are actually very very crucial in computing, yeah, computing things. Like if you want to compute cohomology, homology, uh, yeah, these are the necessary. Yes, length space. So length space is when you take Sn but act by the cyclic group, you get some. Or if you act by S1, then you have to take n to be odd. Then you can act by S1. Then you get the complex projective space. So how do you build algebraic objects out of? How do you do calculations? By using CW complex structure. And how do you get CW complex structure? By having a good complex structure for the original object. So if you're acting by ZP, then you want a Zn equivalent decomposition, and you can guess what that will be. That time I will start with some n points. I'll begin with n points and maybe not 1 point, and then I will sort of combine them like this, and I will build it out of n disks, something like that. Yeah, okay, or whatever. Yeah, k disks at a time. Anyways, this is yeah. Okay, so we'll talk about it later. Maybe yeah. Okay, so I will just if I'm to make a suggestion, I will suggest that try to solve the problems of quotient topology from Moncrief. Okay, so there will be some problems which are like checking and so on, but then there is a in the same, so you can find it where it is in Moncrief, of course. So but then there is a section in that quotient topology which is called topological groups, and that is sort of essential now. It's good time to, and it's also you've already done that, then it's great. Yeah, so have you solved them from Moncrief? Okay, then sorry. James Pancras, yeah, James Pancras topology. Yeah, so if you've solved that, that's very good. Then maybe Vaishnavi, you should solve it, right? So topological groups, there is a section, and quotient topology. So you should solve them, right? Yeah. Okay. Then it's very good. Yes. Yes. I suppose. Yeah. So there is a book, right, by Armstrong, Basic Topology. So Basic Topology Armstrong, and there you will find more than what is there in Moncrief. Okay. Yeah, it has quotient to these kind of things, and then length space is there, and it tries to, yeah, it gradually puts you into this CW complex story slowly, because you can do from Hatcher also, but Hatcher is very terse maybe at the point at this time. So uh, basic topology is in our course in ISI. They first did the basic topology book of Armstrong in the till mid-sem for the master's course in algebraic topology, and after that they went to Hatcher. So yeah, so I maybe that's a wise thing. So we should also do that. Yes. Okay. Okay. So